All right, I'll check. At the risk of being made out to be an idiot, I kind of glossed over this last lesson, and towards the end of it, I kind of guess talked about it a bit. But I genuinely didn't know this, so I think this is kind of cool. If you have a single root, so in other words, like a set of brackets, where are they? A set of brackets, or three different sets of brackets that all have linear terms in them, linear meaning x to the power of 1. If you have single roots, then they cross, so they cross the x-axis. So these three, you'll notice that they cross, cross, cross. The graph crosses the x-axis there. If you've got a double root, it bounces. It says touches, but think of it like a bounce. So like if the double root was here, the graph would go like this and bounce off it. So we didn't actually see an example of that, but suppose it was like something squared and then something and then something. That would mean it kind of goes, and then it might like bounce there, kind of like that would be that one. So that's kind of cool. And a triple root, which we did see, it crosses the x-axis, but it makes a cubic. So with the one that we're looking at here, that is a triple root at 3. So at 3, it makes a cubic graph there. So that's genuinely something I didn't know, because you can find all these little squiggles and curves and stuff using calculus. So I didn't actually know that triple roots and stuff do that. So I think that's kind of cool. Anyway, so that was like a summary of the last lesson. This lesson, what we're going to be able to do is look at the graph of an already graphed polynomial and do stuff to it. So in other words, instead of having p of x, which is just some random thing that I've drawn, so imagine up in the top corner here, I've got p of x. Imagine I've got p of x here. If I find minus p of x, so if I just put a minus in front of it, what that does is it flips it over the x-axis. So you think about x squared, which looks like this. If I have minus x squared, it's upside down. It flips on the x-axis. So here I've got x cubed plus x squared plus x plus 1. That's this cubic curve here. If I put a minus in front of it, that just flips it over the x-axis. Looks like a bit of a strange flip, but it's flipped. If I replace x, every x with a minus x, so if I were to just go in here and replace all these x's with minus x's, what that's going to do is flip it in the other direction. I can't really show that without inputting minus x's everywhere, but essentially that would just put a minus here and a minus there because the squared wouldn't be affected, but it just flips it the other way. So that doesn't really make sense with the x squared example because minus x squared just looks like, so if I put minus x squared, that is just x squared, and that makes sense because when I flip it this way, that's just making the same graph. But with a cubic, it kind of makes sense. Like instead of being like that, it'd be like that. But it kind of looks the same whether it's flipped both ways. So anyway, just if you replace the x with a minus x, it flips the other way. If I add a c on the end, then it goes up or down depending on what my c value is. So if I did p of x plus 5, then that's going to raise the whole graph up 5. So that blue one is the same as the green one, just up 5. And the last one, if I multiply my polynomial by a certain number, that either stretches or compresses it. So these things we already know. These are stuff we've done with quadratics. So you would have already seen this stuff. It's just that we're applying it to every polynomial in existence because everything we learned about quadratics is really transferable to everything we know about polynomials. So if I just times my polynomial, so I've got a k here. If you just watch the red one, if I increase it, you'll see that it's just kind of compressing it and it's raising it. So my value here is 4. It used to cut at 1. Now it cuts at 1 times 4. So like up here. And if I make it lower and lower and lower, oh, I can't because there's no, like if it's a decimal value, then it would stretch it out, but I can't show that here. Okay. So this is all we're going to do. I've got a graph. I'm not told what it is, but to me it looks like a cubic. We could probably find it considering I know its intercepts. In fact, I know exactly what this thing looks like. It's y equals x plus 1, according to this, x minus 1, according to this, and x minus 2. So that is quite literally this graph. If I want to draw each of these transformed graphs, then I can do that. So the graph is just replaced with minus px. So what I do, maybe I'll draw the graph. I normally like to draw the original so that I know what I'm kind of aiming for. So I'll draw the original. Looks like that. Well, that's not bad, eh? Okay, so that's p of x. So then negative p of x will just be the flipped version. So instead of cutting up here, it's going to cut here now. Go like that. There's a real skill to drawing these. And then we'll go through there, up there, and like that. Okay, so it kind of looks like a bit of DNA. And so that's negative p of x. B. I should have really copied that, shouldn't I? Oh well. That's also not bad for freehand. So negative p of x just flips it the other way. So here we go. Let's do this. So like, hang on, is it like this? Oh yeah, that was good. I should have kept that. Like, that's could probably do better. What does the solution look like? Oh, that's completely is that heaps different? Yeah, it is heaps different. I didn't even flip that. It's meant to start. Gee, I'm heaps good at this, eh? Okay, so if I were to flip that, would that not be up there? Yeah, so that'd be there. And it would come all the way down. And then it would go up. And then like that. That should be maybe higher. And that should be maybe a little bit lower. What is that circle that's come up on the bottom of my screen? Go away. Is that Siri? Okay. Cool. Cool little crystal ball that wouldn't go away. I'm not an Apple user, so don't yell at me if I don't know what that is. Whoops. Sounds like the Screamo playing. Is that heaps loud? Anyway. Well, these aren't bad, eh? Alright, p of x plus 2. Oh, that's easier. That's just raised up 2. So 1, 2. Like that. It originally cut at 3, so this would be 5. And that's kind of the only piece of information I need there. Okay, 3 times p of x. So that's going to kind of compress it, and all the values are going to be stretched, like this way. So compress this way, stretch this way. So it cuts at 3 at the moment. So this is 3. So now it's going to cut at 3 times 3, which is 9. So then that's where it cuts. So that means it goes up like that, probably like this. Something like that, perhaps. Say the graph looks like that. Actually, no, it should probably have the same x-intercepts. There we go, which means that one is terrible. That should be here. Let's try that again. Wow. Try and maintain the x-intercepts. It's the y-intercept that's going to be affected. Because when you think about it, oh, I didn't draw it. Remember I had all those sets of brackets? If I just chuck a 3 out the front, that doesn't change what the intercepts are. It does change the output, which is why the y-intercept changes. Oh. Alright, well that's it. Hopefully your graphs are much better than mine. End stream. Oh, that's it. That is our last lesson. That's going to be online. That's it for polynomials. How sad.